Welcome, this is Information Service Engineering, lecture number 3, Linked Data Engineering. In this part of the lecture, you will learn what it means to understand data that you find on the web. Okay, let's try to understand information. What does this mean? Any idea? Who is Pluto? What means never forget? And then, okay, we have some time given there, 1930 to 2006. So usually this is like, this could be the lifespan of a person. But probably you might already have guessed it. In this case, it's not a person, it was the lifespan of a planet. Wow, you might say. Wait. Pluto still exists, doesn't it? Of course it did. But the point is, of course, Pluto is not a planet anymore. In 2006, it was decided that Pluto, due to several circumstances related to, of course, astronomical expert knowledge that you have to have for that, Pluto is not a planet anymore, but it's a dwarf planet. So therefore, we say, okay, always remember Pluto and never forget that until 2006, this was a planet, part of our solar system. Okay, so how does this work? Understanding information. Just look at the word Pluto. We look at the text and then we try to make some assumptions. We try to form some hypotheses. What does Pluto mean? Is it probably the Disney cartoon character, that dog? Or is it this Roman god of the underworld? Or is it the name of a song by Björk? Is it the name of a ship or what else? Or is it the dwarf planet? So you see, this is ambiguous information, and what we want to do is, of course, we want to solve this kind of ambiguity. And the solution of this ambiguity usually is referred to as disambiguation. This is a process which is rather interesting, and you will see also in the end of these lectures how disambiguation in general will work. Okay, but let's go back to understanding and to knowledge. To disambiguate correctly, we have to know about the meaning, the semantics of this information. So first of all, we have to know what is an entity and what is the entity like. So to what class does it belong? What kind of properties does it share with other entities? And this is where classes come into play. So usually you say, okay, Pluto, you do the so-called entity resolution, you say Pluto is an entity. And this entity that you found is member of a class. So Pluto is member of the class of dwarf planets. Now you might say, okay, dwarf planets are a subclass of planets, while planet is a subclass of some celestial bodies. Wait a minute, wasn't there something among dwarf planets and planets? Yep, so you might ask, really, is this the case? And you might see, no. So dwarf planet, of course, is not a planet. Dwarf planet as well as planet, both are celestial bodies. A dwarf planet, as Wikipedia says, is a planetary mass object that is neither a planet nor a natural satellite, and so on and so on. So it's something different. You see here, it depends somehow how you organize your knowledge, how you put information and semantics in it to make clear that a dwarf planet is not a planet and that these two things are not necessarily related. They are only related by joining together in the same superclass, which is here the celestial body. So therefore, dwarf planet isn't a planet anymore. Okay, how to express and how to represent that kind of meaning, that semantics. Usually you do this with the help of ontologies, and ontologies consist out of classes, entities which are individuals, and relations and stuff like that. We will focus on that and go deeper into that later on. We see there Pluto belongs to several classes. First of all, it's a natural object. It's in the class of astronomical objects which have been discovered in 1930. More or less, Pluto also is some kind of a location, and also it belongs to the class of minor planets visited by a spacecraft. And we have even more information. So, for example, minor planets visited by a spacecraft are a subclass of dwarf planet, which again is a subclass of celestial body. Given these class memberships and given these class hierarchies we have here, the interesting thing, if you represent entities and information, knowledge about entities and classes in that way, is that you can deduce implicitly given information and make it explicit. What does it mean? Via inference, for example, you can find out that by Pluto is in the class of minor planets visited by a spacecraft, and that this class is a subclass of dwarf planet, it must hold that Pluto also is a dwarf planet. And you can deduce this by logical inference. Moreover, since dwarf planet is a subclass of celestial body, you can also deduce that Pluto is a celestial body, so is member of the class celestial body. And moreover, given the class hierarchy of minor planets visited by a spacecraft, dwarf planets and celestial bodies, you might find out that minor planets visited by spacecraft are also celestial bodies. And you do this via logical inference. And there is a mathematical foundation behind that which enables you to do that. And therefore, semantics, or representing semantics explicitly with the help of so-called ontologies, this is a formal representation which allows you to draw logical inferences. Other data structures don't allow that, since there is this formal notation and formal representation based on mathematical logic. So this is one important difference, and this makes ontologies much more flexible than other lightweight data structures, for example. In ontologies you can express much more. For example, you can also express the meaning of some kind of properties. So you have a property, for example, name, radius, discovered, or discoverer. And you see here these properties usually join or relate different classes together. So a celestial body, for example, has a name. And the name of the celestial body usually belongs to the classes of strings. So there you have the property name, and it has the domain celestial body, and it has the range string. Again, a celestial body has a radius, which has the range of integer. Or celestial body has been discovered at some point in time. Or celestial body has a discoverer who usually is a person. These are so-called property constraints concerning the domain and range of properties, and this is additional knowledge that you can express with the help of ontologies. And now we go deeper into ontologies, and you will see that ontologies usually are able to represent semantics explicitly. So therefore, parental advisory, here comes explicit semantics. How do we represent ontologies? Usually in ontologies you define classes. In classes you put things together which share a specific aspect. So for example, in the class celestial body there are celestial bodies, and usually you can create a class hierarchy, which means you also specify relations which relate one class with another class. So here, for example, planet is a subclass of celestial body, and also a planet has been visited by a space mission, for example. So is visited by is then a relation or a property, and planet and space missions both are classes. On the other hand, you have an artificial satellite, which also might be a celestial body, and this celestial body has a part or is part of a space mission. And on the other hand, here you have, for example, mission to the moon, which is a subclass of a space mission, because you can have missions in space to different other planets or wherever. So this is the way how you could, via ontologies, and here in a graph-based representation, represent classes and the relationships between the classes. The interesting thing here is that you can put now additional knowledge to classes. How does that work? So what you can do here, for example, you can define constraints for relations and attributes, and they can determine which values are allowed or which values are valid. So for example, you can define a person and then you say, okay, we have two other classes, astronauts and students, and both are subclasses of person. But for example, these classes have a one-to-one relation, so which means a student is always also a person. The same student cannot be two different persons in the same time, so this is a one-to-one relation. On the other hand, you can say a person has an address, but of course a person can have several different addresses. For example, I might live in the summer somewhere at the sea and I might live in the wintertime somewhere else. And on the other hand, at one address, of course, several people can live. So this is an N-to-M relation. So this is some kind of constraint that you can define. Moreover, you can also define things like, for example, disjointness. If you define the class of person and you define two other classes, women and men, and you say women and men are subclasses of person, then on the other hand, you can also define that these two subclasses, women and men, are disjoint, which means there is no individual in one of these classes which belongs at the same time to both of these classes. Please keep in mind these are theoretical constructs, of course. If you put everything together, of course, these classes then contain instances. And on the large scale, classes and instances together form something which is called a knowledge base. And there you determine, on the one hand, the knowledge about the classes, which is the so-called terminological knowledge, and the knowledge about the individuals, which are gathered or aggregated in some classes. So the individuals, they form the so-called assertional knowledge. Let's have a look at our example. We started the terminological knowledge. We know this already. We have here a dwarf planet, which is a subclass of a celestial body. And we have an artificial satellite, which is also a subclass of celestial body. Now let's have a look at the right side. There you see instances or individuals. And there we have the DBR New Horizons, which is an artificial satellite. And this has a title, which is New Horizons. And this space probe, which is an artificial satellite, has a target or had a target. And this was Pluto, who was a dwarf planet. So there you have knowledge about instances on the one hand, and you have knowledge about classes on the other hand. And together they form a so-called knowledge base. So this is a way how we try to model information or meaning, semantics on the web. But now what we have to do is we have to come up with some kind of a universal representation for this kind of data to fix a formal representation and to fix a formal semantics of that. And this will be subject of the next chapter of this lecture.